Hi, my name is Zijie, and you can also call me Jerry. I'm very happy to present my work, When Should You Offer an Upgrade on Upgrading Mechanisms for Resource Allocation. This is a joint work with my advisors Patrick, Hara, and also my intern mentor Andrew in Oracle Lab. I believe many of you have the similar experience. This is a screenshot of a flight booking website. I paid $78 for a basic economy seat. And there's a message on this website showing that do I want to upgrade to a better seat with an additional $35. So I can try to upgrade to this better seat, pay additional money, or just ignore this message. But this motivates a very interesting question, which is why these industries, especially for airlines and hotels, would like to provide such an upgrading option. To answer this question, we take the hotel industry as an example. Suppose a hotel has two room categories. The daily demand for each room category actually depends on a lot of factors, and therefore it fluctuates a lot. But however, the supply is fixed. The supply is the number of rooms in this hotel, so which is never changes. And therefore, there may exist certain situations like under certain days, the hotel receives a huge amount of basic room requests, but only a few of premium room reservations. And in this case, to avoid overbooking for the basic room and also to avoid wasting premium rooms, so the hotel can consider to provide some upgrading plans to the basic room requests. And this upgrading plan can be with a price to increase the total revenue. So the purpose for upgrading is actually to manipulate the demand of each resource category. A very natural question is that why not directly use a standard price to manipulate the demand? The answer is that it is very hard to do so. So we first claim this upgrading is very easy to get implemented in real because upgrading willingness, which is a likelihood of a customer to accept this upgrading plan given an upgrading price, so which almostly only relies on the upgrading price, customer demographics, and hotel property. But the standard price willingness, it will depend on many other factors such as your competitors' prices, some events nearby, and dates, so which are you cannot control. And therefore, it's not realistic to directly use a standard price to manipulate the demand. And so, let me introduce this triple wing online upgrading mechanism. So, the demand units will arrive one by one, and each one of them will request some resource from the supply side, and the supply side will decide either to accept or reject. If accept, they will give it an upgrading plan with a price. And then the demand side can decide either to accept or reject this upgrading plan. And finally, based on the decision of the demand side, the supply side will allocate the resource. And let me introduce a very simple algorithm for two types case. Assume that type 1 is basic and type 2 is premium. So at each time period t, if the arriving customer is type 2, then we should always get accepted if there's any resource available. And if it is type 1 request, so we need to split into two situations. So first, if type 1 resource has positive availability, then we actually accept this request and offer an upgrade at the optimal price to a non-convex optimization problem. And otherwise, if type 1 resource does not have availability, then this is single leg revenue management problems, and we can apply some state-of-the-art algorithm to solve it. And I have some remarks. Firstly, to solve this non-convex optimization problem, actually we create a method to convert this problem into either a convex optimization in certain cases or derive some closed form solutions in other cases. And we can extend this two-type algorithm to handle n types using some nesting and protection level ideas, so to resulting a regret bound of O n log t. So this is actually a very surprising result because traditionally speaking, if we have a non-convex formulation, then the best regret bound we can get is O square root of t. But here, actually it's a special case because we find some hidden pattern behind this upgrading context, which is we can construct a very complicated and creative martingale to approximate the optimal decision at each time step. And that's why we can do better. So finally, let me introduce the numerical simulation. We have a real hotel data over a whole year, and the benchmark algorithm we are comparing is called DSCP, which gives a closed form for the upgrading price. But there's some limitations. First, it have to know like the exact amount of demand of each resource category. And second, it needs to assume the price elasticity is a linear function, but this is not realistic. So we can see the monthly revenue comparison in this figure, and we can see our algorithm consistently outperforms this benchmark algorithm with an average improvement of 17%, which is substantial. So thank you for listening.